In the previous lecture on energetics, specifically thermodynamics, we looked at enthalpy, or heat content, to determine if a reaction was likely to occur. The second contributor of whether or not a reaction occurs is known as entropy, or disorder. Let's use the Jurassic Park model again. What happens in Jurassic Park when we let Mother Nature have her way? Number one, the fences lose energy. In thermodynamic terms, reactions which are exothermic and lose heat content are preferred. The second thing that happens is the dinosaurs spread out all over the park. In thermodynamic terms, Mother Nature prefers reactions in which energy is distributed among many states. This is known as the term delta S, or entropy, and it is a preferred positive term when we're talking about spontaneous reactions. The idea behind thermodynamics is to determine if a reaction will occur on its own, meaning, is a process spontaneous? Processes in nature tend to lower energy. Electrons that are far away from the nucleus in high energy orbitals will prefer to go to low energy orbitals. Excited electrons will go to ground state. Also, high energy reactants will go to lower energy products spontaneously. Delta H will be negative for these exothermic reactions. Looking at this idea, what will be spontaneous in a room at 25 degrees Celsius and 1 atmosphere? If you have a dish of water, will the dish of water spontaneously evaporate or freeze? Well, you've been alive, so you know that a dish of water at room temperature will eventually evaporate. Is evaporation endothermic or exothermic? Well, let's look at the heat content. We are going from liquid to gas phase, so it is endothermic. Is freezing endothermic or exothermic? Freezing means going from liquid to solid, so delta H is negative, and it is an exothermic process. So if only enthalpy were in charge, a glass of water at room temperature would turn to ice. Obviously, that's not what spontaneously happens in real life. So why does the process that costs energy and is endothermic occur spontaneously at room temperature? There must be something else. That something else is covered by the second law of thermodynamics. The second law of thermodynamics deals with entropy, which has the symbol capital S. And it says that the entropy change of the universe is always positive. We can divide it into the entropy of the system, which is the reaction under study, and the entropy of the surroundings. If the entropy change of the universe is greater than zero for all spontaneous processes, it means when something happens by itself, the universe gets more messy. Delta S can be quantified. It is heat, which is measured in joules, divided by temperature, which is measured in Kelvin. So entropy change has the units joules per Kelvin. Why is the entropy change of the universe greater than zero? More probable. How many ways is your room neat? Well, my mother always said, a place for everything and everything in its place. So to her, there was only one neat way for your room to be. The keys should be on the hook beside the door. How many ways can your room be messy? An infinite number of ways. Your keys might be on the hook. They might be in your coat pocket. They might be on the floor. They might be on the kitchen table. The keys can be many places, and it's more probable that there are many messy ways. Let's look at this in terms of chemicals. How many ways is a solid substance at the same energy? Solids pack in very specific unit cells, and at their lowest energy, there are only a few ways to pack things correctly. So there are very few states with which to distribute the energy. How many ways is a vaporized substance at the same energy? Many ways. Gas molecules at the same average energy can have different position, different vectors, different velocities. So there are many ways to distribute a gas among different states at the same energy. What is the relative disorder of a solid versus a gas? We would say that solids have low entropy and low disorder. Gases have high entropy and a high degree of disorder. Graphing this, where the y-axis represents increasing disorder, we have water or carbon dioxide. Notice that solid is a very low entropy state, liquid is a somewhat higher entropy state, but gases are the highest entropy state by a significant amount for both materials. Gas entropy is consistently high. If we look at entropy changes, for a phase change, when you go from liquid to gas, the arrow in the diagram is going up. The entropy change is positive. If we consider going from liquid to solid, or freezing, the entropy change is negative because the arrow is going downward. Question: determine the algebraic signs of delta H and delta S for the phase change, iodine solid going to iodine gas. All you need is the diagram. Both enthalpy and entropy use the same diagram. Which way does the arrow point when you go from solid to gas? We can also consider the entropy change of reactions. Entropy change, delta S, is defined as the change in the concentration of energy of the system. Delta S is positive when the system energy gets spread over more states. That happens in reactions in which moles of gas are produced. The entropy change is negative when the system energy gets concentrated into fewer states. This happens for reactions in which the number of moles of gas decreases. The entropy change is approximately zero when system energy stays at the same concentration. This may be because no moles of gas are involved, or the same number of moles of gas are in the reactant as in the product. Here are some examples where we can predict the sign of delta S based on the moles of gas. In the first reaction, we have 0 moles of gas going to 1 mole of gas. The number of moles of gas is increasing, so delta S is positive because we're spreading energy out among more states. In the second reaction, we are going from 4 moles of gas to 2 moles of gas. The moles of gas are decreasing, so delta S is negative because we're concentrating energy in more states. In the last example, we have 0 moles of gas going to 0 moles of gas. In this reaction, the entropy change is very close to 0. It's probably slightly positive or slightly negative, but not a very large value. Now it's your turn. What is the value of delta S for the reaction below? How many moles of gas are on the reactant side? I hope you think there are 5. And there are 2 moles of gas on the product side. 5 moles of gas to 2 moles of gas. What is the value of delta S for this reaction? How many moles of gas do we have on the reactant side? I'm hoping you're going to come up with 6. How many moles of gas do you have on the product side? 6. That's unchanged. For this reaction, we have no moles of gas on the reactant side and 1 mole of gas on the product side. Moles of gas is increasing. Please note that entropy change is temperature dependent. Think of it like this. When your room is neat, putting a few objects out of place is noticeable. If your floor is nice and clean and you come back from class and you throw your book bag, your shoes, and your coat on the floor, the mess is noticeable. So a little entropy in an ordered system causes a big entropy change. What if your room's a sty? You've got dirty clothes on the floor, chip bags, soda cans, and you walk in and you throw your book bag, your coat, and your shoes on the floor. Did it get that much messier? Not really, it was already a mess. So a little entropy in a system that's already very random does not change the overall randomness of the system. For those of you who like the math, we can look at it this way. Adding 800 joules to 2 different systems. One system is at 0 degrees Celsius, the other is at 100 degrees Celsius. Notice that at low temperature, the top example, the 800 joules causes almost 3 units of entropy change, whereas at high temperature, the 800 joules causes only about 2 units of entropy change. At this point, I need to go through a math proof with the second law of thermodynamics to prove to you that when something happens in the universe spontaneously, the entropy change of the universe is positive. Some of you don't like that, so if you want to fall asleep for a while, I'll wake you up when we get to the appropriate point. The premise we have here is that the entropy change of the universe is greater than 0 whenever something happens spontaneously, and it is divided into the entropy change of the system and the entropy change of the surroundings. Put the actual definitions in now, where we can use Q system over T system and Q surroundings over T surroundings for the entropy changes. If we do this at constant pressure, we can actually substitute delta H for Q system. For the system side, we can have delta H system over T sys. For the change in surroundings, we can have negative delta H sys. Because remember, the enthalpy change of the surroundings is equal to the negative entropy change of the system. So making that substitution, I have this term right here, minus delta H of system over T surroundings, representing delta S of surroundings. This is our substituted equation. Delta S of the universe equals delta H of system over T system minus delta H of system over T surroundings. It's greater than 0 when something spontaneously happens. Here's something that will spontaneously happen. If we have liquid water at 273 Kelvin and the area around it is at 270 Kelvin, the water is going to spontaneously go from liquid to solid state and freeze. Heat flows spontaneously from hot to cold. We are going to drain the heat away from the water at 273 Kelvin. from the system's perspective, the system has lost heat. From the surroundings perspective, it has gained heat. It is a negative, negative, so their surroundings have gained heat. Now the numerator of this equation is the same. Whatever the system loses, the surroundings gain. What's different here is the denominator. T system is greater than T surroundings. That will make the positive magnitude greater than the negative magnitude. So the entropy change of the universe is positive. Let's try a new example. Let's have some water at 100 degrees Celsius surrounded by a region that is at above 100 degrees Celsius, 380 Kelvin. The water is spontaneously going to boil and go from liquid to gas phase. We will also spontaneously have heat moving from the hot region to the cold region. 380 is hotter than 373, so heat is going to flow into the system. We'll give that a positive sign. Heat will be lost from the surroundings, so we'll give that a negative sign. The temperature of the system is smaller than the temperature of the surroundings. So the numerators are the same magnitude, but the denominators are different. This makes the positive value larger, and the entropy change of the universe is once again positive. The entropy change of the universe is used to calculate a term we call delta G. If I substitute delta S surroundings with the term minus delta H system over T system and multiply this equation by minus T system, I get the following equation here. It used to be a greater than sign, but you may remember if you take a negative times an inequality, it will become the opposite direction. So now we have a less than sign. So the entropy change of the universe can be represented by delta H system minus the temperature times delta S system. And when something spontaneously happens, that will be negative. The sum of those two terms gets its own special name. It's called delta G, and it is known as free energy. When delta G is negative, the system releases energy which can be used to do work. In fact, delta G is negative for all spontaneous processes. That's because a spontaneous process is one that goes to lower free energy. So if we look at this equation here, we should analyze the units a moment. Delta H can be in units of joules or kilojoules. Temperature will always be in units of Kelvin. And delta S is in units of joules per Kelvin. Our energy change will be in units of joules, which is a wonderful unit for energy. So the main message here, and by the way, you should wake up at this point, is the free energy change is equal to delta H minus T delta S, and for all spontaneous reactions, the Gibbs free energy change is negative. So a negative delta G means that things happen. Now, how could we make delta G negative? Well, it would very much help if delta H were negative. So it's good when you have something that goes from high potential energy to low potential energy, because that will be a negative delta H. Mother Nature likes that. It's also good when we have a positive delta S for some phase change or reaction. Within the equation, the term is minus T delta S. Temperature can never be negative because it's in units of Kelvin. So if temperature is positive, and delta S is positive, the entire term is negative. And that's good, because negative delta G changes are spontaneous. So it is good, as far as Mother Nature is concerned, if we go from systems which have concentrated energy to dispersed energy, especially systems where we make more gas. Bottom line here is, when delta G is negative, things happen. And it's good and helps when delta H is negative and when delta S is positive. So let's look at the effect of delta H and delta S. You can sort of think of them like light switches. Delta H and delta S can be positive or negative. Then you've also got temperature, which is kind of like a dimmer switch. You can vary the temperature to vary the effect that delta S has. Our first situation has delta H as negative and delta S is positive. A negative times a positive, because remember this is minus T in front, will make this term negative. If you add two negative values together, what do you get? Always a negative value. So this is a great reaction as far as Mother Nature is concerned. It's an exothermic reaction that spreads energy. It will work anytime and be spontaneous. An example is putting sodium metal into water. It doesn't matter what day of the week it is. It doesn't matter what temperature it is. This reaction will always be spontaneous. It generates gas, which means that delta S is positive, and if you've ever seen it done, things catch fire, so it's definitely an exothermic reaction. We can always get this reaction to work, which is what we try to give you in lab. Reactions that always work. Let's try another combination. Delta H is positive, delta S is negative. That means the minus T delta S term is positive. Can you ever add two positive values and get a negative value? I don't think so. We have an endothermic reaction, which Mother Nature is not thrilled about, that concentrates energy. This will never, ever happen spontaneously because delta G will always be positive. Now we can force it to happen by putting energy in, but all by itself, it will not spontaneously happen. An example is production of hydrogen peroxide. When you go to the beach, there's water and there's oxygen. But together, they do not spontaneously make hydrogen peroxide. There are never any warning signs that say danger of becoming blonde in the ocean. Hydrogen peroxide is not spontaneously made. We're going from 1 mole of gas to no moles of gas. So delta S is negative. Also, if you do bonds broke minus bonds formed, you'll discover that it requires heat. It is an endothermic reaction that concentrates energy. You cannot get this reaction to work spontaneously. You can force it by putting energy in every step of the way, but all by itself, it won't happen. Let's try another combination. Delta H is negative, delta S is negative. That means the term is positive. If you add a negative and a positive, can you ever get a negative? Well, sometimes. The positive value needs to be small. And the way we control this is by making sure that the temperature is low. If the temperature is low, the positive term is small. The negative term wins, and delta G can be negative. This would be an exothermic reaction that concentrates energy. The exothermic part is good. Mother Nature likes that. But concentrating energy in fewer states is not to her liking. An example would be water freezing. If you look at our graph, we're going from liquid to solid, so delta H is negative. Delta S is also negative. So as long as the temperature is low, water will freeze. But that's news for you. Stuff freezes when it's cold. But now you can explain it in terms of delta G. Delta H is negative, delta S is negative. The temperature has to be low in order for the delta H term to win and delta G to be negative. The last combination is delta H positive, delta S positive, which means the term that's multiplied has a negative sign. Once again, we're trying to add a positive and a negative and get a negative value. Can we get a negative value? Well, only if the negative is very large in magnitude. So that means temperature needs to be high. This is an endothermic reaction, which is not good, according to Mother Nature, but it spreads the energy out among many states. So she likes that part of it. Here's an example. Water evaporating. We go from 0 moles of gas to 1 mole of gas. So delta S is positive. It requires energy input in the form of heat, so delta H is positive. A positive only works when temperature is high. So newsflash to you, stuff evaporates when it's hot. Positive reactions work when the temperature is high. To summarize this equation, when we're at low temperature, which means T could be 0, we knock out this term. So at low temperature, delta G is the same sign as delta H. When we are at high temperature, we make this term important. And since there's a negative in front of it, delta G would be the opposite sign of delta S. There is a condition, though, if you're at a situation where the value of delta S is close to 0, it knocks this term out, in which case delta G is the same sign as delta H. So here's the summary. Many students like to memorize this for the test. A negative positive is always spontaneous. A positive negative is never spontaneous. A positive will be spontaneous at high temperature. A minus will be spontaneous at low temperature. Some of you enjoy graphs, so I can also explain it this way. What we have here on the y-axis is the value of delta G. On the x-axis is temperature. In the green zone, delta G is negative, so the reaction will go. In the red zone up here, delta G is positive, so the reaction is non-spontaneous. When we have delta H starting at a negative value and delta S being positive, so the slope is negative, the reaction works every time under every set of conditions. When we have delta H starting out negative, but delta S is negative, the reaction works in the green zone at low temperature. But once the temperature becomes too high, we enter the red zone, and the reaction is non-spontaneous. If we have a situation where delta H is greater than 0, we'll start above the axis, but if delta S is positive, the slope is negative, and we can eventually enter the green zone. Positive works at high temperature. And then there's the poor condition that is always in the red zone. Delta H is positive, delta S is negative. No matter how we play with the temperature, we'll always be in the red zone and the reaction will never be spontaneous. So back to this idea of can we predict if a process will occur on its own? knowing that processes in nature tend to lower free energy. But this time, we know that temperature is important. So let's think about this evaporation or freezing of water at two different conditions, 37 Celsius and minus 10 Celsius. Hopefully you realize that at high temperature, evaporation of water is likely to occur. Why is that? Well, think about evaporation of water. It's from liquid to gas. So that means delta H is positive, delta S is positive. When does positive become spontaneous? At high temperature. So at high temperature, the delta S term becomes important, which means delta G is negative and evaporation occurs. What about at minus 10 degrees Celsius? If it gets cold, water freezes. Freezing of water is liquid to solid, so it is a negative scenario. Negative scenarios occur when we're at low temperature, because at low temperature, delta G goes with delta H. So delta H is negative at low temp, delta G will also be negative. Here's an example of how you can tune a reaction with temperature. I have here a reaction where two NO2 molecules, which are brown in color, can produce an N2O4 molecule, which is colorless. You notice that delta H is negative and delta S is negative. When is negative spontaneous? At cold temperature. So we would expect this reaction to be colorless and make product at low temperature. But if the temperature were higher, we might be more brown in color. I have double-sided arrows here because, as you'll learn, many reactions are reversible, so they can go either direction depending on the temperature. So let's have a look at this and see what we see.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
If we look at the math for this at low temperature, or 15 degrees Celsius, we know that delta G is equal to delta H minus T delta S. So here's delta H, the minus 58.2. 15 degrees Celsius is 288 Kelvin, and delta S is minus 0.177 kilojoules per mole. Delta G is negative. Negative means that the reaction spontaneously goes forward. And you notice that the ice water one was pale in color. It was tending toward colorless. What about the one on the hot plate? Well, at 80 degrees Celsius, now the temperature is 353 Kelvin. So notice how the delta S term has made delta G positive. A positive delta G means the reaction is not spontaneous in the forward direction. So instead, it prefers to be the brown reactant. It's lucky for us that for phase changes, delta H and delta S are always known. We can use this diagram where solid is at the bottom, liquid a little higher, and gas the highest for both enthalpy and entropy changes. Any change in which we're going up say from liquid to gas, means that delta H is positive and delta S is positive. A change where we are going down from, say, gas to solid, both delta H are negative and delta S is negative. So phase changes are always positive, positive, or negative, negative for most materials. Determine the relative values of delta G, delta H, and delta S when water freezes. Something is spontaneously happening. The water is freezing. So what sign is delta G when something spontaneously happens? What about delta H and delta S? Well, all we need is our handy-dandy diagram. Water freezing goes from liquid to solid state. So which way is the arrow pointing? Determine the relative values of delta G, delta H, and delta S when acetone evaporates. Once again, something spontaneously is happening. So delta G has to have a particular sign. And here's our diagram. Acetone evaporating, that would be going from liquid to gas. So which way does our arrow